Hi, I'm Corey Hayden.
And I'm Alex Zamora, and we are two of the engineers designing the control system for Cyclone RoboSub's competition vehicle, Manatee.
The design strategy for our system called for rapid testing and iterative changes to our control system in parallel with hardware, electrical, and embedded programming work. It was critical that holdups in these areas didn't delay the overall progress of our control system. This requirement informed the various MATLAB features our team leveraged to complete our project. Our first objective was to build a digital model of the robot in Simulink. This model is broken up into four major components: the plant, the sensor models, the signal processing unit, and the controller. In the plant, a thruster model maps the commanded motor signals to thruster forces on the rigid body and uses MATLAB's built-in vehicle dynamics model to calculate the resulting vehicle states like position and Euler angles. It also accounts for gravity, buoyancy, and simplified hydrodynamics. This use of built-in, well-validated Simulink blocks for certain elements of the dynamics and sensor models was key to our team's success. These blocks greatly reduced the development time and allowed our team to focus heavily on the control strategy and less on the underlying mathematics. In the sensor subsystem, we use MATLAB's built-in inertial measurement unit model, along with custom models for the depth sensors, downward-facing camera, and Doppler velocity logger. These models use statistics from tests or the sensor's datasheets to simulate the noise and bias and apply them to the simulated true states from the plan model. These sensor noise models are critical to assure that the control system we design in Simulink will perform similarly in hardware. The goal of the signal processing unit is to take information from the sensors and camera model and to perform state estimation for the vehicle's position and orientation in the pool. Here again, the built-in MATLAB models for the extended Kalman filter in the attitude heading and reference system saved hours upon hours of development time. Finally, the controller uses 6 PIDs to generate motor commands based on the estimated states along with the current mission objectives.
Our submarine model is only useful if the performance of the digital twin accurately reflects the real system. To this end, Simulink's parameter estimation tool was indispensable. The three most important parameters for a plant model are the inertia matrix, the hydrodynamic added mass matrix, and the drag coefficient matrix. For complicated systems like our robot, these values are very difficult to determine analytically. Fortunately, the parameter estimation tool allowed us to take real sensor and motor command data our team collected during pool testing and perform a least squares estimate of these unknown parameters that map motor commands to vehicle dynamics. Here is an example using the tool to estimate the drag coefficient on one face of the vehicle. We used case studies like these to learn the parameter estimation tool with simulated data before using it on our real vehicle. In the simulation, the vehicle's thrusters are turned off and it begins at a velocity of 5 meters per second. Due to the quadratic drag coefficient set to 30, the forward velocity quickly decays to 0. Using the thruster forces of 0 as the input and the velocity measurements of the output, we see the parameter estimation tool quickly converges to the correct drag coefficient, even with a bad initial guess. With an improved dynamics model, we can use the PID auto-tuning tool to tune the 6 PID controllers to the desired step response with the click of a button and 0 trial and error. With our controller performing well in MATLAB, one looming problem remained. All the complicated signal processing and control code needed to run on the Raspberry Pi onboard computers in C++. Thankfully, MATLAB had the solution. Almost all the C++ code for signal processing and control that our robot runs was automated using MATLAB's code gen capability. This feature saved countless hours of writing, testing, and debugging that would have added unacceptable delays to our design. As a new club, this is the first year we are competing in the RoboSub competition. I can say with certainty that without MATLAB, our team would not be ready to compete this year.
On behalf of the Cyclone RoboSub team, thank you MATLAB for giving us the tools we need to succeed.